So, welcome to this problem solving session on of the course Basic Electronics, coded NOC 23 EE62. This is week 8. Today is March 25. My name is Amit. I am a PhD scholar at IISc Bangalore. And for the past 7 sessions, we have been trying to solve the problems of some previous year assignments for this course. In the first session, we had talked about the Thevenin and Norton equivalence, nodal analysis, superposition theorem. Then in the second session, we saw some transients RC and RL and how does the switching change the waveform of these transients. Then we moved on to diodes and diode-based circuits like clamper, peak detector, and so on. In session 4, we saw half-wave detectors implemented using diodes, and then we quickly moved on to the BJT circuits and their DC biasing. And in the subsequent session, we saw the same biasing to implement a common emitter amplifier using BJTs and their small signal models, primarily the hybrid pi model and the T model, and their interconvertibility. Finally, we saw one more application of BJTs, that is push-pull amplifier. And then one of the most prominent circuits which is used is the op-amp circuits. In the session 6, we talked about the ideal op-amps, while in session 7 we had introduced some non-idealities in the op-amp circuits, and also the difference amplifier we had talked about in the last session itself. In today's session, what we'll be primarily focusing on is the you can say the frequency response of an operational amplifier. So we'll begin, but just a quick summary of the operational amplifier. As the name suggests, it's required to perform some operations, namely comparison, integration, differentiation, addition, subtraction. And we had seen some of these applications like integration and addition and comparison. And usually it amplifies some input voltage, and it's a subclass of differential amplifier. For that, we need to see how a very simplified differential amplifier looks something like this, which you can see on your screen on the left. And this is the voltage expression for such a differential amplifier. However, if we design, in order to convert differential amplifier to an op-amp, you need to have AD greater than AC, where AD is the differential gain that you can see here. Why this is called differential gain? Because you see the voltage that is being multiplied is the difference of two input voltages. Must be greater than AC. AC is also referred to as common mode gain, and this is the AC term, and this is multiplied by the average of the two inputs. So you can see there are two inputs here. This is the negative input, this is the positive input, and the output is taken in such a fashion that the difference of the drain voltages of these two BJTs. Also, we design the circuit in such a manner that the output impedance is high and the input impedance is low. And finally, what we get is an operational amplifier, which is denoted using this symbol on your right. So there are some properties of an ideal operational amplifier, which you can see in this table. So open loop gain is infinity. It can go up to infinite voltage, and the key things which I have to take away is the input impedance is infinity, but the real value is some mega ohms. Output impedance is 0 ideally, but it does have a practical circuit does have a few ohms of output impedance. And this we saw the non-ideality is the offset voltage, the offset current, and the bias current. Ideally it's 0, but real value is a few millivolts. And some of the things that are again repeated is the slew rate. Slew rate is the rate at which the output changes. So it's usually denoted by volts per microseconds. And similarly, there's another term called common mode rejection ratio. Remember that I had just talked about AD upon OC. So CMRR is defined as 20 log AD upon AC. So if AD is much higher than AC, then this number will come out to be like 600 or 100, depend on the magnitude. If it's 3 orders higher, then the answer will be 60 dB, which is a decent operational amplifier. Right, and this ideal value is infinity, because you'll have AC equal to 0 and AD is some very high value, but practical values are 60 to 100 dBs. And so this is the equivalent circuit for a depiction of an op-amp rather, where the output voltage is given by this expression. AOL is the output loop gain multiplied by the voltage difference at the inverting and non-inverting inputs. And plus minus V that you see here is nothing but the saturation voltages, right? And so some of the very common circuits is the comparator circuit. We have seen this multiple times. You apply a reference voltage to one of the inputs, and if Vin is greater than Vref, you get plus Vsat. If Vin is less than Vref, you get minus Vsat. You are in this region. However, somewhere in the middle is your is the linear region. Yes, Kadu. Okay. R naught equal to 0, then V naught equal to 0 always, right? Okay. No, V naught is not 0. V naught will depend. So let me just go to the circuit again. Okay, we can see it here. So you see, even if R naught is 0, if you see R out equal to 0, then you can see that V out is given by G times V in, or by this formula, right? Even if R out is 0, it's given by this formula, V out equal to gain times the difference of the inputs. So depending on the value of inputs, the output voltage value will be decided. So it will not be 0. The drop will be 0. This means ideally whatever the amplification is, that all amplification will go to the output voltage. Okay, so its output voltage is not 0. No, so by V, which value are you talking about? I'm talking about here V out here. V out is dependent on R out, because a current will be flowing here. If you connect some load, there will be some current flowing through this, depending on the direction, there might be some current flowing, so there might be some drop. It's not that V out is completely independent of R out. It is depending on the current flowing. But in ideal case, if we take R out equal to 0, so whatever the amplification is, that whole amplification will be reflected at the output node here. There will be no loss inside the, and you can say there will be no loss inside the circuitry of the op amp itself, to put it very crudely. Yeah, V equal to IR is the drop that you will see here. So if R out equal to 0, there will be no drop that's happening here. So V out, you can clearly see will be G times V in, where V in is the difference between the inverting and non-inverting, the values of voltage applied at inverting and non-inverting terminals. Okay, so there's no drop here in that case. V equal to IR drop. Okay. Fine. Now let's move ahead. So we saw the comparator circuit, which operates in these two regimes, saturation, but often we want amplification. Here you cannot get amplification, you will get a constant voltage. So we want to operate in this linear region, right? And to facilitate that, we provide feedback, usually negative feedback, because this is stable output. Some of the examples we saw were integrator and differentiator. However, sometimes you also want an unstable output, an oscillating output. A common example is Schmitt trigger. This I think we will not cover in this session, but I think in the next session we have some circuits and problems related to Schmitt trigger and oscillators. So we'll talk about positive feedback then. But then that's a very short summary of the operational amplifier idealities and their very basic applications. Now we'll quickly jump into the problems for today. So the first problem that we have today is talks about the relation between which of the following plot correctly describes V out versus Vi. Output voltage noted here, input voltage noted here. Relationship for the circuit shown in the figure. So this is the circuit that we have. So if you identify, this is a Zener diode. This is a Zener diode. So I'll just quickly so this is the diagram, and you can see that. So before solving any op amp based questions, there are a few pre-checks that I try to follow. First is, ask yourself the question, is the op amp ideal or not? Okay, we talk about the op amp ideality. So in this problem, the question is silent about the ideality of op amp, so we'll assume it to be ideal, and this assumption is important. We'll see in a short while why it is so. Secondly, check if there is any feedback, because as we just talked about, if there is no feedback, then usually it's in comparator mode, and the output will be plus or minus Vsat, right? But if there is feedback, then it will be either oscillating if it's a positive feedback, or if it's a negative feedback, then you will see it can give a stable output, right? So in this feedback, you can see the output node is connected to the inverting terminal, the negative terminal, through some circuit. It's 2R and a diode here, right? So feedback is there, and it's a negative feedback. Alright, based on the information that we have, if it's an ideal diode, this means no current can be flowing inside here or here, right? Because remember, in a couple of slides before, we said Rn equal to infinity, so no current can flow here for an ideal op amp. Similarly, there will be no voltage drop here. We just talked about that R out is 0, so no voltage drop. So whatever V out that we'll get will simply be the gain, that is the difference between these two. But there's a feedback also, so we'll have to solve this circuit accordingly. And you can see that this circuit is inverting amplifier, right? Because the input is being fed to the inverting terminal. Okay, and the third condition, based on, since no current can be flowing here and it's a negative feedback, is the condition of virtual short. What's virtual short? Virtual short is effectively means that these two are at the same potential, approximately at the same potential. This arises due to the fact that that we can write, I'll solve this here. This we can write that we know that V out, we saw that is given by A, which is the gain, times V plus minus V minus, right? And we know since this will be operating in the linear regime, right? So we can write V plus minus V minus equal to V naught over A. V naught will be somewhere between plus and minus V sat, and this value, I'm not denoting it here, but this, there will be some plus V sat and there will be some minus V sat. This is usually 10 volts or 15 volts, but the value of A is 10 to the power 5 or even higher. So this value is approximately 0, very small, few microvolts. So what this effectively mean is that V plus is approximately equal to V minus. V minus is this voltage, V plus is this voltage. This condition is known as the virtual short, which is denoted by here. What this means is that this node and this node, both the inputs of these, the inverting and non-inverting inputs of the op-amp are almost at the same potential. Note the word almost. Okay, and this is a very interesting feature, and which we'll frequently use to solve the circuits relating to the op-amps. All right, so these are the three things that we'll keep into mind. And in this problem we also have a Zener diode. All right, so how does a Zener diode perform? So we know that, so let me first draw this is the ID, current through the diode, and this is the, let's say, the voltage on the x-axis, VD. Okay, so let's just try to see in the positive direction. The Zener diode behaves like a typical diode. So this means that characteristic will look something like this, and this is what we also known as the VNE, right? In the opposite direction, we know that the current remains, there is some leakage current which we see, and suddenly the current increase and the device is said to have broken down, right? This is what we call as the breakdown voltage, and in Zener diode this is also known as the VZ. Usually what happens, there are two kinds of breakdown, the Zener breakdown and the avalanche breakdown. This is a Zener diode. Usually avalanche breakdown devices sometimes break destructively, means they cannot be reused in the forward direction. The beauty of Zener diode is that it can be used in this breakdown condition also. Note that the current will be very high. This current here is few nanoamps. Okay, very small leakage current. Current here will be few milliamps. All right, so this diode even can be used, and current also here usually is a few milliamps after VNE in the positive direction, in the positive side, positive bias. This is forward bias in the first quadrant, reverse bias in the third quadrant. So even you can use the Zener diode in this mode also, and the voltage, the beauty of it is that the voltage will remain fixed. This means it behaves like as if a voltage regulator. The voltage cannot increase further, but the current can be increased, obviously up to the limit that we do not burn the Zener diode. But to summarize, so this is how a Zener diode looks, and it can work even in the forward direction as well as the reverse direction. So these are the two key takeaways that we have. Okay, so now using this information, now we'll go ahead and try to solve this circuit. Okay, so this is the diagram that we are given. So this is T, and we are required to find V naught, the relation between V naught and Vi. So what I'll do is that we'll first take the first case, and that is when Zener diode D is forward biased. Okay, so I am assuming the Zener diode D to be forward biased. This means I'll transform this circuit now. Okay, so V input will remain the same. This is Vi, this is your op amp, minus plus V out, this is your load resistor RL, non-inverting terminal is grounded, and there is a feedback resistor 2R. And now what I'll do, I can replace this diode, since it's forward bias, I can replace this with simply a voltage source of 0.7 volts. Okay, I'm replacing this with a voltage source of 0.7 volts. And also please note that there is a virtual short condition, right? So this is V minus, all right, and this is V plus. So I can write that using virtual short, V minus equal to V plus, approximately equal to V plus, which I can say is 0 volts since V plus is grounded. All right, now what I'll do is I'll draw the currents. Okay, so let's say current I1 is in this direction. Let's say this current to be I2 and this current to be ID, and note that no current can flow here because we have assumed an ideal diode. Okay, so now what I'll do as the next step, so we'll call this step 1, and we'll apply KCL at inverting input node. Okay, so if I do that, that will be incoming current, that is I1. This should be equal to outgoing current, that will be 0, this current, plus I2 plus ID. I2 is flowing here and ID is flowing in this direction. So what's the value of I1? If I apply Ohm's law across this resistor, I can simply write Vi minus 0, because this voltage is 0, remember, Vi minus 0 upon R. This is equal to, the value of I2 will be 0 minus V0 over 2R. This is the resistor 2R, 0 minus V0 plus ID. This is some current ID that is flowing. Okay, but even before that, you can clearly see from this that if I apply KVL, or you can simply see over here that this is 0 volts, right? And if I see this means V0. So I can directly say that looking across diode D, if I look across diode D, I can simply say that its P terminal is connected to V minus. So V minus is N terminal connected to V0. V minus minus V0 is nothing but 0.7 volts. This battery, right? This will give me V0 as minus 0.7 volts. So rather than doing through this, you can directly obtain the value of V0 over here. Here there's a variable ID. So what we can do essentially here is that we can also obtain an expression for ID. That's not required in this case. So for when Zener diode D is forward biased, right, we get V0 equal to minus 0.7 volts. But now we have to identify, remember that we are required to find V0 as a function of Vi, but we still have to impose a condition on this Vi, right? So till what time will it be forward bias? It will be forward bias till the time the current is flowing, ID is positive and I2 is positive in this nomenclature. Because if ID is positive, this means this diode is conducting, and if then this drop is 0.7 volts and I2 will also be positive, right? So I can clearly see that this means that the condition that will be imposed is that ID must be positive, right? Because then only we can say diode is forward biased, right? So you can obtain the value of ID from here. Okay, so what we can see simply is that it will be Vi by R plus V0 over 2R must be greater than 0. That's the condition. Okay, so we can now clearly see that Vi from here must be greater than minus V0 by 2. This means Vi must be greater than, so value of V0 is 0.7. So if you put this here, it will get minus 0.35 volts. So now we can see that for the first half, the case 1, when the diode forward bias, for Vi greater than 0.35 volts, the output should be 0.7 volts. Okay, so I'll write that case here. So I'll write this here, case 1 summary. What is the case 1 summary? If Vi is greater than 0.35 volts, this will give us V out as minus 0.7 volts. So this is the thing that we have to keep in mind. Okay, now let's talk about case 2. The case 2 would be case 2, diode is reverse biased. And even in reverse bias, what I am talking about is before breakdown. What this would mean is that no current through diode. This means ID should be equal to 0. There's no current flowing. So how will the circuit diagram look like? The circuit will change to something like this. This is VI, this is R, RL, V0, this is 2R, and this is grounded, and again this is virtual short. Okay, so if there's no current flowing through here, now you can quickly see that now this is the typical inverting amplifier that we see, and we know the result for such an amplifier, the output and input relation is given by V0 equal to minus RF by R. RF is the feedback resistor, so that's 2R over the input resistor, that is R, times VI. So I can say V0 equal to minus 2 VI. So this is the second case. So this, you can see it's a linear relationship between them, right? But we also have to see that the breakdown has not reached. We have taken the second case to be before breakdown. Okay, so this is V0 equal to minus VI, but there's a condition imposed. That condition is that VD must be less than 0, right? Because it's reverse bias, and I'm defining VD as this VD. Okay, but it should also be greater than the VZ. It should be less than the magnitude of VZ, where VZ is the Zener breakdown voltage for this diode. All right, so VD should be less than 0, and it should be less than 0 and should be greater than the negative of the VZ. VZ is usually denoted as a positive entity, so hence this negative sign. Okay, so let's do that. What's the value of VD? Now VD again we can see is nothing but minus V0. See VD, this again terminal is connected to 0. This is V0. So VD I can see is nothing but minus V0. So minus V0 has to be less than 0 and has to be greater than minus VZ. So if you sort this out, you can clearly see that V0 is nothing but minus 2 VI. Okay, VD is minus V0, and if you place V0 is nothing but minus 2 VI. So this will give us less than 2 VI less than 0, and this will give me that VI must be less than 0 but must be greater than this must be greater than, just give me a second, minus V so minus VZ over 2. So this is the condition. Okay, so VI must be less than 0, right? But it must be greater than minus VZ by 2. So VZ value can be anything like 10 or 20 or whatever. So but this is the condition that we have to follow. Okay, so now I'll write case 2 summary here. Case 2 summary, what is it? This is case 1 summary. So case 2 summary, I got V0 equal to minus 2 VI for VI less than 0 but greater than minus VZ by 2. Now let's do case 3. I'll use a different color for this. Okay, so now let's do case 3. So what is case 3? Case 3 is the third scenario where a diode is in breakdown. Diode is in breakdown. This means current can flow. How will the circuit diagram look like then? Op amp will remain the same. This is positive. Here is the input side. You have a 2R resistor as feedback. This is the load resistor. This is the output. And now remember, now it's the reverse bias, so the polarity has to be changed. So it will look something like this, and this magnitude will be VZ, right? And note, this time the current will flow in this direction, reverse bias. Okay, earlier we saw in the case 1 current was flowing in this direction, left to right. Now the current will flow from right to left. Okay, So now again we can clearly see that now this is due to virtual short, this is again, so we can again see that V naught here in this case is nothing but minus Vz. You can clearly see, if you see that this Vz is nothing but the diode voltage, so V naught is nothing but minus Vz. So very straightforward case for this. So again we can write case 3, we obtained, excuse me, case 3 we saw V naught equal to minus Vz, but there must be some condition that's imposed on Vi. What is that? Let's see that now. So so the condition imposed will be Vi is that diode must be reverse bias, and reverse bias so much that it has entered the Zener breakdown mode. So how do we do that? We know that Vd is nothing but minus V naught, which in this case is Vz, right? And yeah, so but we have to link it with a relationship from Vi, right? Now if the current is flowing in this direction, now if you apply KCL at this node, okay, if I apply KCL at this node, I can write that I1, again I1 is the current flowing here, this is the ID, and this is the current I2 flowing through 2R resistor. So I can write I1 incoming current plus I2 plus ID should be equal to 0. There's no outflowing current in this configuration. This gives me ID equal to minus I1 minus I2, and this entity should be positive because the current has to flow only in this direction. Okay, now if you do that, if you calculate the value of I1, so I1 can be written as minus Vi over R, and I2 can be written as V naught, I2 can be written as V naught minus 0, right? So that will be V naught over 2R. This entity should be positive, and if you solve it further, you can clearly see that Vi from here, it will come that Vi must be less than, it will come out to be Vi must be less than minus V naught by 2. This implies Vi must be less than, so value of V naught minus Vz by 2. So Vi must be less than Vz by 2. This we put it here. All right, so now we have completed all the 3 sets. Okay, so so there will be a minus sign coming here because we are playing with the magnitude. So Vz here we have taken it to, the polarity is reverse, so there has to be a negative sign here, right? So this goes something like this. So now what I'll do, using this information, I'll write this information again on the next slide, and then we'll see how the waveform looks like. Okay, so first case was that I'll write this here. V out was given by minus 0.7 volts when Vi is greater than 0.35 volts. Okay, in the second case, or it's given by minus 2 Vi, okay, for Vi less than 0 but Vi greater than some minus Vz by 2, and finally when Vi is less than minus Vz by 2, this is given by a constant minus Vz, right? So this is what we are seeing over here, right? So now let's just try to see for some positive value, let's say 10 volts, V in is 10 volts. When V in is 10 volts, we should see a minus 0.7. Okay, so that gives me this, I think something like this. Let's assume this value is 0.7, minus 0.7, right? And let's say some Vz is, let's say some 10 volts. Okay, so for very negative values, the output voltage should be the output voltage, yeah. So for very negative values, the output voltage, note again, kindly note that the Vz that I am using here, so you have to be careful about the notations that I am doing. Okay, so because Vz I have treated it in this manner, so what we can see here, so this is the notation, so notation will matter. Okay, it's not like that it doesn't matter here. So this is 0 anyways. You can see this is the virtual short, and here this is the value V naught that we have. Okay, so you can see that, so it will be 0 minus V naught, so V naught will be at a smaller potential, right? And this is the value Vz that we have seen. Okay, so we can see that it's coming out to be at some negative voltage. It will so in the middle region it will have a negative slope, right? It will have a negative slope, and you can see this is the negative slope that I'm talking about here. And for some negative voltage it will keep on rising, and finally it will saturate. So there must be some plus sign coming, because this is the graph that is matching our data. So our correct answer would be B. So the thing to notice is that you have to break down this Zener diode for three regions: when it's forward biased, when it's reverse biased but before breakdown, right? And finally when diode is in breakdown, and then huge amounts of current can flow. And this we obtained, the condition on VI we obtained due to the fact that ID has to be positive. So that was the thing that propelled us to identify the proper voltage. Okay, so it's plus Vz. Why it's plus Vz? Because I've already reversed the polarity here. Okay, so that's why. So Vd must be equal to Vz, right? So again here it will be, yeah, it will be minus V0 by 2, so hence it will be minus Vz by 2. So that part is correct. So V0 is plus Vz. Okay, so it's plus Vz, and so we obtain the curve B. So just keep into mind this. You just have to put the conditions on this diode D, and you will identify three cases in this case, right? And you can clearly see, just like a comparator graph, we saw two saturations in one linear region, right? It's the same case over here. So you can also see that the voltage is clamped at some, so this is some voltage Vz, right? Some voltage Vz. This is also acting as a regulator. The voltage cannot rise above Vz. Vz can be 10 volts or 15 volts, right? And you can see this voltage is anyways minus 0.7 volts, which we obtained over here. And this is the you can see, you can use in this region for amplification purposes, right? Which we use typically for an operational amplifier. All right. So B was the correct answer, and now we'll quickly move forward. So this is the second problem. Says, what is the form of the transfer function? The transfer function usually given by this V0 upon Vi, and as a function of j omega, where this j omega term come because we want to talk about everything in terms of impedances. All right. So now let's see this problem and try to sort this out. You can see that this format looks a bit familiar, in the sense that this is a difference amplifier. All right. So what I'll try to do is that we'll try to solve this problem over here. So how do we do that? Again, I'll assume that the op-amp is ideal and there's a virtual short condition, right? So what I'll try to obtain is first this potential V plus, right? And this potential V minus will naturally be equal to V plus. So as first step, find out V plus. So just to be clear, we are required to find out this. Okay, what's the formula, and then we can simply see the form what it looks like. So find out V plus. How do you find out V plus? You can see it's a potential divider. It's a potential divider at non-inverting input. If you use the potential divider, you can simply write V plus equal to R1, which is this impedance, divided by total impedance that is being seen from here. So I am essentially using this circuit. Okay, I can write R1 plus, it is in series, so there will be a plus sign, and the capacitors can be converted into the reactance using 1 upon j omega c. This whole thing multiply the input voltage, which is Vi. So you can see Vi is the voltage that is being applied over here, right? So now what we can do is that now we can find out V minus, which is nothing but equal to V plus, right? Due to the virtual short condition. We have seen the virtual short condition. When the op-amp is ideal, there can be no currents that are flowing in, and in case of a negative feedback, if it's operating in the linear region, we'll see that these V plus and V minus are approximately the same, which is known as the virtual short condition. Okay, now as a third step, what we'll find out is V out is what? So how do you find V out? Let's assume this current here is I1, this current here is I2, right? So how to find out V out? V out, we see that KCL at inverting input. Let's do that. KCL inverting input. So incoming current is I1, outgoing current is 0, no current can flow here, so 0 plus, this is the other outgoing current, 0 plus I2, I1 equal to I2. What is the value of I1? I1 I can simply write as Vi minus V minus, this node is V minus, over R2. This must be equal to the value of I2. I2 is nothing but Vi minus V0. This is the potential drop over R2. So R2 and R2 get cancelled. What I get from this is V0. I take this V0 to the left side. So I'll get V0 equal to minus Vi plus twice of V minus. These two terms will add up. Alright. So Vi is a independent variable, that's fine, and V minus is nothing but V plus, which for this I have a expression over here. So I'll write this properly here. It will be minus Vi plus twice of V minus, so twice of this term, twice of R1 over R1 plus 1 over j omega c times Vi, right? But remember, we have to obtain the expression of V0 over Vi, right? That's how we express this this transfer function, right? That's the way we want to express it. So I can simply write that this gives me V0 upon Vi. I'll take Vi common from here, that's it. So it will be 2R1 over R1 plus 1 upon j omega c minus 1, right? That's it. Now just taken minus 1 on this side. This is what we have the transfer function. There will be j omega term, I mean these here also, but you can see this is the way it looks like. Okay, so I'll copy this to the next slide. So we have obtained that H has come out to be 2R1 upon R1 plus 1 upon j omega c minus 1. Now what I'll do is that first of all I'll take R1 common from the top, from this first term. So it will be 2 upon 1 plus j omega rc, R1c rather, right, minus 1. And I'll define, what I'll do is that I'm defining R1c as omega naught. Okay, this is the this is what I'm taking it as. So it will be 1 upon 1 plus, sorry, it will be 1 upon omega naught, because this is in units of time. So 1 upon omega naught. Okay, so it will be yeah, so this will come out to be omega naught by j omega, right? Yeah, that's correct. Okay, so now we'll take the LCM as j omega, right? Yeah, so what it will come out to be, 2 times j omega upon omega naught plus j omega minus 1. If you solve it even further, it will come out to be 2 j omega minus omega naught minus j omega upon j omega plus omega naught. So one of the j omega gets cancelled out. What we'll get is j omega minus omega naught upon j omega plus omega naught. Okay, now again we want to reduce it in terms of, so j omega by omega naught. So what I'll take omega naught common from the numerator and denominator both. So what I'll get is j omega by omega naught minus 1 over j omega by omega naught plus 1, right? Now we can see we are closing in on these forms, right? And then finally, if I take minus 1 common from the top, it will be minus 1 times 1 minus j omega by omega naught divided by 1 plus j omega by omega naught, correct? So we can see it's matching 1 minus k, if option B. You can see minus at top, plus at bottom, so that is the option B, that's matching. K value is minus 1 here, right? So you can also the question can also ask us what is the value of k. So we find that out. So this was a fairly straightforward problem to find the transfer function. We simply first find out the value of this the voltage of the non-inverting terminal, and then since by virtual short we know this terminal will also be the same, then we apply the KCL and finally obtain the expression for, so rearrange some terms, finally obtain the expression for transfer function. Then there's some more algebra, and then finally after taking the LCM, this is the format that we found out, right? So you can clearly see it has 1 0 and 1 pole. So this is the 0 that you can see, and this is the pole, right? We'll see a bit more of these terms when we try to plot the magnitude and phase. So these terms will reappearing in our discussions. Okay, right? So moving on for the next question, it says that for the op amp filter, so it's a filter, it must be filtering something, some frequencies. the filter type and the 3 dB frequency are respectively. Okay, so we are required to find what is the filter type. So is it low pass, band pass, high pass, what is it, and the corresponding 3 dB frequency. Right, so what is 3 dB frequency we'll talk about, but first let's just try to figure out the filter type over here. Now again, as I do, we'll do some pre-checks and we'll assume that the op-amp is ideal, right, because the question is silent. We'll assume the op-amp is ideal. This means no current is flowing over here or here. And then second, we can see it's a negative feedback, right? So negative feedback usually gives us the stable output, right? And if we are operating in linear region, and if we are indeed operating in linear region and it's an ideal op-amp, we arrive at something called the virtual short. Virtual short means the inverting and non-inverting terminals are almost at the same potential. V plus is approximately equal to V minus. Knowing this information, now first I'll try to find out what is the, just a second, yeah. So knowing all this information, I'll first try to find out what is the transfer function. How does it look like? Because then only we can determine the type of the filter, right? So that's the first step. This is the first step. Okay, find H J omega. Right, how do we do that? We just simply replace it with the corresponding impedance, right? So first let's do that. Let's transform this circuit. So this is R1, negative, positive. This is grounded. V0. It will be RL here, and what we have here is this is connected. This is R2, and we have. So what I'm going to write it as is I'm going to write this as a block of ZC, right? But the value of ZC will be 1 upon j omega c. I can also write it as ZR, right? So here Z equal to R2, Z equal to R1. There is no reactive part over this. There is no imaginary part because these are only the real part remains. Okay, so now what we can see is that now these two are in parallel, right? So now what I can do is that I can again redraw this circuit as something like this, and which will be a very familiar circuit now. So let's draw this as Z equal to R1, and there is a impedance here also, and let's call this ZL. This is V0, this is grounded. So let me just delete this fellow. Yeah, so we have input from here which is being fed here, right? And this is, we can call it as Z effective, where Z effective is nothing but, I call this Z1, Z2. Z effective is nothing but Z2 parallel ZC. These two are in parallel here, right? And we know what the this is nothing but a non-inverting amplifier. So the output for this we know looks like something like this. The gain V0 upon Vi is the feedback circuit impedance, which is minus Z effective divided by minus Z1. This is Z1, right? So so now what I try is I just need, sorry, this is plus Z1, so I just need to find out the value of Z effective. Okay, so let's do that. So Z effective would be Z2 times ZC over Z2 plus ZC. Very straightforward. So it will be R2 times 1 upon j omega c divided by R2 plus 1 upon j omega c. Now if you solve this, it will come out to be R2 over 1 plus j omega R2c. This is Z effective, and the value of Z1 is nothing but R1. So this essentially comes out to be minus R2 over R1 times 1 plus j omega R2c. And this is your V0 over Vi, which is also the H. Okay, so this is the output that we have figured out. So I'll write this on the next slide. So we have obtained H j omega equal to minus R2 over R1 divided by 1 plus j omega R2 times C. Now the questions asked what is the filter type. So how do we see what is the filter type and what is the 3 dB frequency? So the way to do that is you apply different values of omega, which is the frequency here, right? So let's say we obtain very large values of omega. Large compared to what? So first we need to find the R2C, which is the 3 dB frequency. Okay, so I can write omega naught is nothing but 1 upon R2C. So let's just try to find out what this value is, so that we have a numerical idea. So it's 8.2K times 50 nanofarad, right? Let's just put these values in the calculator first. So it will be 8.2 times 50, that's 410. So it will be 1 upon 410 micro, right? So if I do that, let me just do this. So it's a 2.44. This is coming out to be 2.44. Because a micro goes up, it becomes mega. So, and I've used 3 of them, so it will be kilo radian per second. Let's just see that I've done it correctly. So kilo times nano, it will be, yeah, micro. So micro, if it's there, it goes up, it becomes 10 to the power 6. I've used 10 to the power 3. Yeah, 2.44 kilo radians per second. So that is the that is in terms of radians per second, but you see the options is given kilohertz. So we know that omega is 2 pi f. So we know that 2 pi f naught is 2.44 kilo radians per second, right? So what I can do now, I can find out the f naught from here. That will be, so this 2.44 divided by 2 and divided by pi, this comes out to be 0.388 kilohertz. 0.388 kilohertz, this will be 388 hertz, which is the option B over here. Oh, sorry, I mean, it can be B or it can be A. I should not say it's B, because you have not determined the type of filter, but it's not these two options. So C option and D option are eliminated. It's either A or B. So how do we find out whether it's low pass or high pass? What we do is that, so what we now will do is we provide an omega much higher than 2.44K, right? So what I mean is that now this term is in the form minus R2 by R1, 1 plus j omega by omega naught naught. 1 by R2C is omega naught. So I'm writing in this form. Now what I'll do, I'll provide omega, right? I'll provide omega greater than omega naught, right? So let's say omega equal to, this is 2.44K, right? So let's say I provide 25 kilo radians per second. So what's going to happen? This term will be very large, right? This will be approximately 10, right? And so we can ignore 1. So you can see the output, right? The output would be then, in this case, the output would be minus R2 by R1 divided by 10, right? 10J. If you only talk about the magnitude, so mod of J would be R2 by R1 divided by 10. And if you take 20 log, then this will be falling, right? This will be much smaller than your constant. So, and let's take the other case, omega less than omega naught. By that mean omega is it was 2.44, right? So let's say 0.25 kilo radian per second. In that case, omega is lesser than omega naught, so this term will be vanished. So mod h will come out to be R2 by R1, right? R2 by R1. So R2 by R1 is 8.2, right? Here it will come out to be 0.82. So what's happening is that, so let's draw it in this fashion. So this value is omega naught, this value is 0.1 omega naught, and let's say this value is 10 omega naught. So for omega less than omega naught, it remains constant at 8.2, right? So this is mod h. So it remains constant at 8.2, something like this, right? And only after omega crosses at higher values, you say it's 0.82, so it's somewhere here. If I provide it, let's say 250 kilo radians per second, it will be even lower, something here. And if you plot it in log, right? If you plot it in log, this will look something like this, right? So this value would be log 8.2, and it will keep on falling like this. So what's happening is that for low frequencies, the gain is high, log 8.2. As you increase the frequency, the gain keeps on falling, and gain will even go on negative. This means that this is no more amplifying, this is attenuating. You don't want that. right? We only want amplification if that's the application. So what we see is that for low frequencies, it is letting the signal pass, the gain is high, but for higher frequencies gain is negative. This type of filter is known as a low pass filter because it's only allowing low frequencies to pass, and hence the option would be B. The key way to identify low pass filter is this format, 1 plus j omega by omega naught. If this is the term, this is the format, like some constant over 1 plus j omega by omega naught, this is typical of a low pass filter. Okay, so the way we solved this problem was we identified that this was a very simple circuit in the sense that it's a non-invert, it's an amplifier with the input being fed to the inverting input terminal. So that's an inverting amplifier which with the gain as minus Z effective by Z1, where Z effective is the effective impedance for these two components which are in parallel. We obtained that, and finally we obtained this expression where we find out the value of omega naught, which came out to be 2.44 kiloradians, and in hertz it's 388 hertz. So much lower than 388 hertz frequency, the gain would be high, but as you keep on increasing the frequency, this term denominator will continue to increase and the gain will continue to fall. Hence this is the characteristic of a low pass filter, and that's why we get the option B. Okay, right. So now let's move forward, and okay, so this is the problem similar to before, not exactly the same. We are again required to find the function of hj omega, right? So we are required to find hj omega, the transfer function, how it looks like. Again, you can identify, again I'm not repeating the same things, that there is a virtual short condition because we are assuming it's an ideal op amp, and the fact that it's operating in linear regions. So all those things see into the picture, and we see that this is an inverting amplifier, and we know that for an inverting amplifier, gain is nothing but the feedback, that's R feedback over Rn. In other terms, sorry, minus R feedback over Rn. We can also write in this case is Z feedback over Zn. So what are Z feedback? This is your Z feedback, and this is your Zn. Okay, so let me redraw this circuit in the terms that I mean. This is Zn minus plus, this is grounded, this is Z feedback. Okay, and this is V0, and here is your load ZL. This is your input over here, right? What is the value of Zn? Z feedback we know, straightforward. Z feedback is nothing but R2. Zn is something we have to find out. How do we find out Zn? Z is nothing but series component of these two components, right? So I can simply write Zn equal to R1 plus the component, this component is 1 upon j omega c. Okay, so I can just rearrange these terms, so I can write it as 1 plus j omega, I just take the LCM, j omega R1c over j omega c. Just taken the LCM, and let's put this value of Zn over here. This will come out to be minus R2 divided by 1 plus j omega R1c divided by j omega c, and this whole term will come out to be minus j omega R2c over 1 plus j omega R1c. Okay, so this is the gain, or H. This is the expression, right? So I'll take this to the next slide. H is coming out to be minus j omega R2c over 1 plus j omega R1c. Okay, but we want in these terms omega 1 and omega 2. So let's define omega 1 and omega 2 first. Okay, so what I'm going to do is alright, let's define that. Just let me just make sure that I've done it correctly. So it's Z feedback over Zn, it's minus R2 over Zn. Zn is nothing but series component, so R1 plus 1 upon j omega c. It's correct, so it will be j1 plus j omega R1c over j omega c. J omega c will go on top, minus j omega R2c upon 1 plus j omega R1c. Yeah, this is correct. Okay, so we have obtained now this form, but we want it in the format of so you can see that we have a term in the numerator, in the denominator we have only one term, right, j omega r1c. Okay, and in the numerator we have a okay, let me just first let me just simplify this. Okay, I divide it by, so I take omega naught as 1 upon r1c. Okay, let me first do that. So it will be j omega r2c over 1 plus j omega by omega naught. This is what I'm defining as omega naught. Okay, now what I'll take is, I'll take j omega, I'll keep j omega inside and j omega by omega naught, and I'll take minus r2c outside, and this I'll define as k. So k is minus r2c. So now I'll get the form h equal to k j omega over 1 plus j omega by omega naught, so which matches, the form matches with the option D over here, as you can see, right? The value of k, where I can write, where k is minus r2c and omega naught is 1 upon r1c. It matches the option D. Again, to summarize, a very straightforward problem. This is an inverting amplifier that has been given. We know that the gain is the feedback minus r2 over this combination, and we find this combination as r1 plus 1 upon j omega c. Rest is this just algebra and rearranging the terms, right? Right, so now let's go on to the next problem. Again, we have to find out the transfer function. Again, I'll assume an ideal op-amp. This means a virtual short condition and no currents are flowing in. So let's do that. Now in this case, you can see it's a non-inverting amplifier because the input is being provided to this terminal, right? So what I'll do is that, let's do this virtual short. Let's call this voltage V plus, so this is V minus. Okay, so in the first step, find out V plus using potential divider. If I do that, I'll get V plus as R divided by R plus 1 upon j omega c, because again what I'll do is I'll replace this with the component of impedance 1 upon j omega c. This impedance will remain the same, right? So if I do that, so times Vi, this is the value of V plus, and using virtual short, V minus will be equal to V plus, and then if you directly use the formula of non-inverting amplifier, right, using non-inverting amplifier formula, you can get V naught equal to 1 plus R2 upon R1. This is the feedback divided by the input, R2 by R1 times V plus. This is the formula for that. So I'll just simply put the values R2 by R1. The value of V plus is this, that is R over R plus 1 upon j omega c. Okay, what I'll do is that I'll take no, I'll do it on the next slide. So we obtained that H equal to 1 plus R2 over R1 times R divided by R plus 1 upon j omega c. I'll take j omega c as the I'll take the LCM over here, so it will come out to be 1 plus R2 over R1 j omega rc divided by 1 plus j omega rc. Okay, again what I'll take omega naught equal to 1 over rc. So this format will now reduce to 1 plus R2 over R1. This will become j omega by omega naught over 1 plus j omega by omega naught. So this is the format that I am getting. Okay, let me see something matches. Okay, A is matching. I'll tell you how. So you define as, so what I'll do is I'll do now like this, 1 plus R2 by R1 by omega naught. So I'll take this omega naught over here into j omega by 1 plus j omega by omega naught, and I'll define this as k. Okay, so you can now see k times j omega or 1 plus j omega by omega naught, which is option A. Again, which we have been seeing this over and over again in these problems. is that you just replace C with the corresponding impedance and you solve the circuit like before. So this is a very straightforward problem again like that. All right, now we jump to problem 6. Sorry, 6. 1 second. Yeah, problem 6. Right. So in this question says an op-amp circuit is shown in the figure along with the input voltage waveform. This is the waveform that you're seeing on the input side, which graph correctly depicts the output waveform. So again, I'll assume that this is an ideal op-amp. And diode will not assume ideal, we'll assume a semi-ideal diode, which means is that in the so this is how a diode will look like. Okay, so we'll assume this is 0.7, this is VD, and this is ID. In the reverse bias, we'll assume that zero current is flowing. Okay, so this is the diode that this is the function. This is the IDVD characteristics of the diode that I'll take. All right. So so first I'll do is that I'll take the case 1. What's the case 1? D is on. D is on means diode is conducting. This means that there is some current flowing over here, which I denote by ID. Okay, since this is an ideal op-amp, right, and again assuming the virtual short condition, which we can assume this is a negative feedback circuit, right, and we are assuming this is operating in the linear region, right. So V plus will approximately be equal to V minus, which is also known as the virtual short condition, right, and I am assuming that no current is flowing inside the op-amp. Okay, because this is an ideal op-amp. All right, so if no current is flowing inside this means there is no current flowing over here. So no current can flow here, and there is only one path. This means whatever ID is going, it's going over here. Correct? That's the only pathway for the current to flow, right? So D is on, right, and this node is nothing but, I'm denoting it as V out. This is the output voltage of this operational amplifier. Remember, the output voltage of this operational amplifier is denoted by gain A times V plus minus V minus. Please remember this. This is different from V out, which is over here. Okay, so so if this is the condition, so what I'll do is that first I'll redraw this circuit. Okay, I'll redraw this circuit as this minus plus. This is yeah. So this will be behave just like a battery because the diode is on. Okay, this is R. This is V naught, and this is nothing but VI, right? And this is a virtual short. Remember that. Okay. So what I am getting is that, and yeah. So this is I denoted as VD, right? So VD in this case is 0.7 because diode is on. VD is 0.7 volts. Okay, so you can clearly see now this, if this is virtual short, this will be VI, and so output voltage can be clearly be seen is nothing but V minus, which is nothing but VI. So output voltage will be nothing but the input, whatever the input side is. Okay. Secondly, we also saw that this current ID flowing like this. There's no current flowing here. I equal to 0, right? So from this I can also write. So this is the first step. As the second step, I can write that applying Ohm's law across R, what I see is that V naught is nothing but ID times R, right? ID times R, so ID is nothing but V naught by R, which is nothing but VI by R, and ID has to be positive because we assume diode is on, so this has to be positive. This means VI must be greater than 0. I am assuming positive resistances only. So only for VI positive, right, we can see that V out is equal to VI. So let's do that. So how will it look like, the output waveform? Let's draw with a different color. Okay, so how will it look like? So for VI positive, only for VI positive, V out should be equal to VI. This is VI positive till this region, right? And again from here to here. Okay, only for the positive half cycle of Vi, Vout will be same as Vi. So what this means is that this will look something like this, and then it will go down to 0, and then it will go something like this, and then it again go down to 0, right? So this is Vout as a function of time. But note that this is only the first case. We also have to consider what happens when the diode is off. This is just half the picture. So let's talk about the second half of the picture, right? So that is the case 2. Case 2, D is off. Okay, again we still have this virtual short condition, right? Okay, as I was talking about, I defined it as V out. Okay, and this time this diode is off. So let's see how so if this diode is off, no current can flow here. This means that no current is flowing here, and no current is flowing here also. Correct? ID equal to 0. This I equal to 0, this implies that IR is also 0. So what I'll do is KCL at V naught. So incoming current is ID, outgoing current is I plus IR. This is I, this is IR. ID is 0. I is 0 because ideal diode, plus IR. So IR comes out to be 0. If IR comes out to be 0, if I apply Ohm's law, this means V naught equal to IR times R. That also comes out to be 0 volts. No current is flowing over here, right? But there has to be some condition, right? So we'll see that condition if we redraw this diagram. Minus plus. Okay. This is V naught. This is R, and this is Vi. Okay, so this is V out, the output of the op amp, and we know that V out is nothing but A times V plus minus V minus, that is Vi. What's the value of V minus? V minus is nothing but V naught, right? And V out we know is 0. Okay, so what's going to happen is that so the way to do is that we know that this diode has to be reverse biased. This means that V out, the positive terminal, must be at a lower potential than the negative terminal. Negative terminal is V naught. Okay, so V out must be less than V naught. What's the value of V out? V out is nothing but A times Vi minus V naught, right? V naught we already know is 0. Okay, so if I replace this as AVI must be less than V naught, this will give me Vi must be less than V naught by A. And if I assume very high gain, this will approximately be 0. So this implies for Vi less than 0, for Vi less than 0, this analysis is valid. D is off. Vi less than 0. So if I draw for Vi less than 0, Vi less than 0 means negative half. Okay, so for this reason the diode is off. And again for this time diode is off. Okay, so now what I'll do is I'll try to combine the both graphs. So we saw that for negative cycle, for positive cycle, the output, which I'll draw in red again here. So we saw that output was following this, like this. For negative cycle, for when Vi is negative, output was 0, and then again this, and then like this, and then again 0, and then again it will rise. So it's like for positive cycle it's conducting, for negative cycle it's 0, which matches with our option. Okay, so this is the correct option for question 6. Okay, you just have to follow what the diode is on or off, and then split it into two cases, and we try to figure out the value. Rest is very simple op amp, like the virtual short and just the KCL, and we'll be fine. Now the problem 7 states that an op amp circuit is shown in the figure along with the input voltage waveform. Which graph correctly describes the output waveform? So this is a circuit with an op amp, and you can see there are two diodes. So we'll assume the diodes to be semi-ideal, which would mean that their characteristics, which is, by that I mean IDVD, is of the form of this. So this I assume at 0.7 volts, and for negative bias I am assuming they have 0 current. okay, while they turn on only at 0.7 volts. So this is true for D1 as well as D2. Okay, and now we want to analyze the circuit with, for the given this triangular waveform as the input, we want to find out the output over at this node. So right, so before that, just a few assumptions that I'm assuming that this op amp is ideal. This means there's no current flowing in either of the inputs, and the second thing is that I'm assuming the virtual short condition, which we can assume in this case, since if I assume that this is operating in some linear region. Okay, so now starting with these assumptions, now let's quickly jump in. I'll take so this is the circuit that I've reproduced. Let's take the first case when I assume that D1 is on and D2 is on. Mind you, this is an assumption that D1 is on as well as D2 is on. So this circuit can now be transformed in this format. See, all the resistance op amps remain the same except that now this D1 and D2 both are replaced by a voltage source, and these are the currents, and I can also say that this voltage is 0.7 volts. Similarly, this voltage source is 0.7 volts, both of them, right? So first what I'll do is that since I've assumed a voltage drop of 0.7 volts across each diode, now if you first carefully look across D1, this is the D1 diode, you can see here. So I can write its positive terminal minus negative terminal should be equal to 0.7. Positive terminal is this, which is sitting at 0 volts due to the virtual short, minus V out, which is I have assumed the potential of this node to be V out. This should be equal to 0.7 due to the fact this is the diode D1. Okay, sorting this out, I get V out equal to minus 0.7. So this is an important data point. Similarly, if I do the same exercise for D2, it's again similarly for D2, I can write V out minus V naught, P minus N, voltage at P side minus voltage at N side should be equal to 0.7. This gives me V naught as minus 1.4 volts. So this is again an important data point. So this node is minus 0.7 and this is minus 1.4. Okay. Now moving forward, what I'll do now is I'll apply KCL at this node, at node V naught. So what I'll do, all the incoming current, which is I2 plus ID2 should be equal to outgoing current, which is IR here. So let's write the expressions for I2, ID2 and IR. Okay, so first we'll rearrange the terms at ID2 equal to IR minus I2. Just rearrange the terms, and this is the important thing. This should be greater than 0. Why? Because we have assumed D2 to be on. If D2 is assumed to be on, then this ID2 should be positive, right? So IR minus I2 should be positive. Now I place the value of IR, which is V0 minus 0 over R, just Ohm's law, minus I2, the value of I2 is 0 minus V0 over R2. This should be greater than 0. Right, so this simplifies to V0 over R plus V0 over R2 should be greater than 0, and R and R2 are positive quantities, so if you take them common, the only thing it will be positive only when V0 is positive. Okay, note that here we are obtaining, so let's this is 1 and this is 2. Now if you compare 1 and 2, 1 says V0 should be minus 1.4, 2 says V0 should be 0. Cannot be true, right? But we obtain V0 equal to minus 1.4. Wrong assumption. So here I am comparing 1 and 2. Okay, comparing 1 and 2. This is a wrong assumption. So D1 and D2 both cannot be on simultaneously, right? Now taking the second case where I assume D1 to be on and D2 to be off, this means this is on, well this is not conducting. The circuit diagram will look something like this. So everything else remains the same. Here there is a drop of 0.7. Okay, these are the currents, but this is open circuit. All right, this node is again at V out, sitting at V out, right? So like previous case, I'll again assume 0.7 volts drop across D1, and similarly if I say 0 minus V out, this time this voltage is V out equal to 0.7, I obtain V out equal to minus 0.7 volts. So this node is sitting at minus 0.7 volts, correct? Similarly, I'll again apply KCL this time again at V0. So this you can say I2 equal to IR. There's no current flowing from this branch, so I2 should be equal to IR. What's the value of I2? I2 is 0 minus V0 over R2. 0 minus V0 over R2. IR is V0 minus 0 over R. Again, I rearrange the terms. I take V0 common. So 1 plus R2 over R equal to 0. This is possible only when V0 equal to 0. So V0, this node is sitting at 0 volts. And if this is 0, then you can also obtain the value of I2 and IR using these expressions. They will also come out to be 0. So effectively, this is 0, this is 0, this is 0. No current can be flowing through the resistor R2 and R, which makes sense, right? Because both the ends of this resistor are sitting at 0 volts. Same goes for R. So there's no current flowing in this branch. Okay, but there is some current which is flowing in I1 as well as ID1. It might be flowing, correct? So let's try to evaluate that. Now what I'll do, I simply apply KCL at node A. So it will be I1 equal to 0. So this is the current, no current is flowing here, right? This denotes that 0 plus I2, this current, plus ID1, this current. So 0 plus I2 plus ID1. We already know I2 is 0. We have obtained it here. So I'll drop this term. This becomes 0, right? And ID1 simply becomes equal to I1. Now ID1 equal to I1, and this should be greater than 0. Why? Because D1 is on. Remember, we have assumed D1 to be on. This entity should be positive. So ID1, which is I1, I1 should be positive. Now what's the value of I1? I1 is simply V0 minus 0 over I1. Sorry, V0 minus 0 over R1. So V0 minus 0 over R1 should be positive. R1 is a positive quantity. This gives me the condition that Vi should be positive. Okay. So we have obtained that Vi should be positive. If Vi should be positive, V0 is 0 in this specific case. But we still have to verify one more thing, and that is that this should be reverse bias. How do we see that? Again, we see that the voltage at the positive terminal should be higher than voltage at the negative, should be less than the voltage at the negative terminal, right? Pn. So voltage at P is V out minus voltage at N, which is V0. This should be negative. Only then D2 will be reverse biased. This is the condition. We know the value of V out. V out is we obtained minus 0.7. So minus 0.7 minus 0 should be less than 0. Minus 0.7 should be less than 0. This is true mathematically. Hence, our assumption is correct. Okay. So whatever we had assumed in this case, all the things are consistent with each other. There is no discrepancy. There is no contradiction. This implies that this assumption is correct. So what we have found out in this case, when D1 is on and D2 is off, Vi is positive. Vi you have to apply. Vi is positive, and it is the case that V out is coming out to be 0 volts. Now we move on to third case when D1 is off and D2 is on. The circuit diagram will look something like this. So you can see D2 has become open circuit and D1 is replaced by a voltage source of 0.7 volts. ID2 is the current flowing through this diode D2. Again, I'll apply KCL at node A. So if you do that, it will be I1 equal to I2 plus 0. I'm assuming no current is flowing and no current is flowing here also. So I2 plus 0. You place the value of I1 as Vi minus 0 over R1. And I2 is 0 minus V0 over R2. You get V0 equal to minus Vi because R1 and R2 are same. You can see both are 1K. So V0 we get minus Vi. Inverter. That's the equation for an inverter. Right. Now that we have done that, now let's move forward and we'll apply now KCL at V0. If I apply KCL at V0, incoming current is I2 plus ID2. This is incoming current equal to IR, which is the outgoing current. I'll place their expression. So I2 is 0 minus V0 over R2. ID2 remains the same. We don't know the expression for that. And IR is V0 minus 0 over R, right? I'll rearrange the terms. So ID2, if you take V0 to the other side, it's just like R and R2 are in parallel, right? Because this is V0 and this is ground as well as this is ground. Okay, so V0 R plus R2 over RR2, this should be positive. Why this should be positive? Because D2 is on. Remember that. This is the case when D2 is on. So if this is positive and this is a R and R2 both are positive. So what we'll get? We should get V0 should be greater than 0. Correct? V0 should be positive. And we know V0 is minus Vi. So you place it there and you get Vi should be less than 0. This is the condition that we have obtained. For Vi less than 0, V0 should be equal to minus Vi for this specific case again. Only for this case. Right. So now we have done that. So we have obtained that this is in on condition, but there's still something remaining, and that is to verify whether this is in the off condition or not. Okay. To do that, first we'll we'll find out the potential of this node. Okay. How do we do that? We know there's a 0.7 volts drop across this D2 diode. So I can write its P terminal, which is V out, minus its N terminal, this P terminal, N terminal. So V out minus V0 should be equal to 0.7. Because I am assuming drop to be 0.7. This gives me the value of this V out node as V0 plus 0.7. So whatever the value of V0 is, V0 is a variable, it depends on Vi, right? It should be V0 plus 0.7. Okay, now I can apply that reverse bias condition across this diode, across T1. So we know that D1 must be reverse bias. That's what we had assumed, right? D1 is off. So Vi, so it's positive, it's P terminal, which is sitting at Va, which is the voltage here, minus V out, it's N terminals voltage, which is here. Right, this should be less than 0. Only then this will be reverse biased. Right, P terminal should be less than N terminal. So I place the value of Va, which is 0. V out, it remains as it is. and the expression for V out we have obtained here, V naught minus 0.7. So you plug this value over here, you rearrange the terms, you get V naught should be greater than minus 0.7. okay, V naught should be greater than minus 0.7. This would mean now I'll use this expression, V naught equal to minus Vi. Okay, V naught is greater than minus 0.7. Now if I replace V naught by minus Vi, we get Vi less than 0.7 volts, and this condition already says that Vi should be less than 0 volts. Okay, so these are consistent with each other, hence this is a correct assumption. You can say or you can say it either way, that you take the common for the intersection of these. So the intersection of these is Vi is less than 0. Essentially what I am saying is that if Vi is less than 0, for which we did this analysis, this is true, this holds true, because this is an overbearing condition. Even for Vi less than 0.6 this will work, but here we are not even going that high. Vi is less than 0. Okay, so in this case, when D1 is off and D2 is on, we see that when Vi is less than 0, output voltage is simply inversion of the input voltage. Now let's consider the final case when D1 is off, when D1 is off and D2 is also off, both are off. Okay, this is how the circuit diagram will look like. I've labeled all the requisite currents. So what we'll first do, we'll apply KCL at this node. So you apply KCL. So again, I1 equal to I2, since there's no current flowing here and no current can flow here, assuming it's an ideal diode. Ideal op-amp, I1 equal to I2, you write their expressions like before, and again you get V naught equal to minus Vi. Again the expression for an inverter. This happens because R1 equal to R2. Remember, they have the same magnitude, so it gets cancelled out. Now I'll apply the KCL at this node, V naught. So incoming current, which is I2, should be equal to outgoing current, which is IR. The expression for I2 you can write is 0 minus V naught over R2, and the expression for IR is V naught minus 0 over R. You again rearrange the terms, you get this term. This is 0. R and R2 are both positive quantities, so this can never be 0. The first term V naught then has to be 0. If V naught is 0, and we can also see that correspondingly I2 and IR both will come out equal to 0, just like we saw in a case before. So V naught is 0, I2 and IR both are 0, correct? So now we have obtained the currents and voltages. Now we are required to test the conditions, whether these are indeed reverse biased or not. Alright, so let's first do the reverse bias for D1, this diode. So its P terminal minus N terminal voltage should be negative. Its P terminal is disconnected to A, so VA minus V out should be negative. That's the value of VA. VA is at ground, minus V out should be less than 0. Okay, you rearrange the terms, we will get V out is greater than 0. Alright, this is the first expression for V out. Now I'll again do the same thing for the diode D2. The diode D2, its P terminal is sitting at V out, its N terminal is sitting at V naught, which is 0. So what I'll do, I'll again, for D2's reverse bias, V out minus V naught should be less than 0, just like with this here. This will give us V out is less than 0, V naught value is 0, remember, this is 0. So V out should give me less than 0. Here I am getting V out is greater than 0. Here I am getting V out is less than 0. This is a contradiction, right? Both cannot be true simultaneously. Hence, this assumption is wrong. So in this configuration, this circuit will never work. Okay. So what we did is that we saw the 4 configurations. That's all the combinations, and we saw in two of the combinations we are the circuit is not even working, right? So to summarize, what we got, that V naught was minus Vi, and in this case Vi was less than 0. Okay, when Vi is negative, V naught V naught was minus Vi, and this was the case when D1 was off and D2 was on. Similarly, other case which did not give contradiction was when D1 is on and D2 is off. In that case, we saw output to be 0 provided the input is greater than 0. So these are the only 2 cases that survived without any contradiction. Now let's try to plot them. So let's take when Vi is less than 0. When Vi is less than 0, output is inversion of Vi. So this is the case. I'll use I'll use the red color itself. So when Vi is less than 0, this means we are talking about this part. Okay, in this part V out is inversion of Vi, so V out will look something like this, inverted, right? It's a triangle, sorry about that. Okay, so now we have drawn it. Now let's draw the second part when Vi is positive. When Vi is positive, V out is 0. So in this region V out is positive, this means V out should be 0. Here again it will be 0, and here again it will be like this, and again 0. So this is your V out. So what we are seeing is that flat triangle, flat triangle. So flat triangle, flat triangle. So option C will be the correct option for this question. Now just to summarize, this was a problem given to us with two diodes. We took all the four cases, right, where one is off, the other is on, and we solved. We used different, so we applied KCL here, we applied KCL here. Using KCL, we saw that when they were on, that the current should be positive, right, because they only conduct in this direction, for instance, and this one in this. And when they're reverse bias, their P minus N voltages should be negative. So if this is reverse bias and the voltage here minus voltage here should be negative, only this it will be reverse bias. Using all those conditions, we saw that only two cases survived, which are these, and we obtained these results for them, which we have plotted for option C. So in this case, an op-amp circuit is shown in the figure with the input voltage waveform, which graph correctly describes the output waveform. So input waveform is given, we are required to plot the output waveform. Alright, so again I'll assume case 1, as we always do. D is on. Okay, when the diode is on, I'll just quickly draw the circuit diagram, how it looks like. This is R minus plus, this is ground, this is R. If the diode is on, so it looks something like this, right? And then this is the second diode that we have, and this is like this. Okay, this is also R. Okay, so if the diode is on, this means this means there's some current flowing over here in this direction, ID, what I call. Okay, so this is a virtual short, so this voltage will also be grounded, and this is VI, right? Okay, so if whatever current is flowing through over here, let's call this voltage something. Let's call this voltage V0. Okay, this node I'm calling as, no, not V0, let's call this V1, because V0 is already there. This is V1. Okay, so let's just try to figure out what will be the value, this value V1. Okay, so there is some current flowing in this direction, what I'm assuming, right? So what I'll try to do, and the same current will flow here, because remember this is an ideal diode, no ideal op-amp, no current can flow inside. So whatever current is flowing here, the same current will flow here, right? And also note that no current can flow in this, right? So I am assuming this current to be I2, this current is I1, right? So what's going to happen is that I1 equal to I2, first of all, I1 equal to I2, because this is called op-amp 1, let's call this O1. O1 is ideal, O1 is ideal, right? And I2 must be equal to minus ID. Why? Because O2 is ideal, no current can flow inside O2. So I2 must be equal to minus ID, right? And ID, current can only flow in this direction, please note that, right? So what this means is that now I'll try to write the expression for I2. So I obtained ID is nothing but minus I2, okay, which is the same as minus I1, and the expression for I1 I can write as, I1 is this, so this will minus VI minus 0 over R. So this comes out to be minus VI by R. So ID I obtained is minus VI by R, and we know that this has to be positive, then only this diode will conduct, correct? Yeah, only then this diode will conduct. This implies VI has to be negative. So only when VI is negative, this diode is conducting, right? So this is the first case, but we also have to see what's the value of V0, because that is the thing that is of importance to us, right? So you can clearly see that again I1 equal to I2. So if you do that, that's VI over R. This is nothing but 0 minus V1 over R. I'm just doing I1 equal to I2. Okay, so this will give me V1 equal to minus VI. So this node is at minus VI. Very simple expression. So this node is at minus VI. If this node is at minus VI, again by virtual short, this is also at minus VI. So this implies V0 is also at V0 is at V0 is at V1, because of this is nothing but a buffer. Buffer is operational amplifier 2. So I get V0 equal to minus VI. V0 equal to minus VI, but the condition is that at this condition. Okay, so that's the condition. Now for the case 2, we do D is off. Okay, D is off. So let's draw the circuit again quickly. So this is VI, resistor R, this is operational amplifier 1, and this is resistor R. Now what's going to happen is that this will now behave like an open circuit, correct? And this is R, this is my second op amp, where this is V0. Note this is what we have been taking as V1. This is again R and R. This node will be at 0 because of the virtual short again. So whatever, so we know that O2 is buffer. This will give us V0 equal to V0 equal to plus V1. Whatever, so we just need to find out the voltage at this node, correct? Now let's draw the currents. This is I1, this is I2, right? No current can flow here, remember that. So I1 must be equal to I2, right? And again, no current can flow here and no current can flow here. So this implies that I1, which is equal to I2, must be equal to 0. Why? Because we have considered ideal op amps and D is off. Whatever current is coming has to flow here, but this current cannot go in either of branches. So this means I2 necessarily has to be 0, correct? If I2 is 0, now what is I2 necessarily has to be 0, correct? So if I2 is 0, what that means is that there is no voltage drop over here, right? So this means is that V1, I2 is 0, which is equal to 0 minus V1 over R. This will give me V1 is also 0. So V1 is 0 volts, right? This will give me that V0 is at 0 volts, right? So what we have obtained is that give me a second. So this diode D is off, right? If D is off, so whatever current is coming, whatever this current is, right? So what's going to happen is there are two ways of seeing this actually. Let me do this the proper way. Yeah, so what we'll try to do is we'll try to impose a condition on this. So remember, this is the V out for this operational amplifier, and we can see that V out for this op amp for O1, this is O1, this is O2. For O1, V out will be nothing but A times V plus minus V minus, right? This is V out, and for ID has to be reverse bias. So for that, for D to be off, we can see its positive terminal has to be lower than the negative terminal. This implies that V out must be less than V1, correct? V out must be less than V1. So what's the value of V out? V out is nothing but A times V plus minus V minus, and in this case V plus is nothing but 0 and V minus is nothing but V in, right? So I can write minus A times Vi has to be less than V1, right? So what is that? So in the last case we saw Vi was negative, right? V1 is 0, we just saw that. So this implies Vi has to be positive. This means for positive Vi, okay, for positive Vi, this is the case. What is the case? V0 should be equal to V1. What should be the value of V1? Now there's no voltage drop, so this potential is V1 naturally, right? This potential is V1, so there's no virtual short in this condition. Why? Because this pathway is not complete. Okay, so in this case this virtual short will not work. So in this case V0 will come out to be V1, which will come out to be Vi. So V0 will be equal to Vi for Vi greater than 0, and we saw that V0 was minus Vi when Vi was negative. So I'll write this here. So V0 is plus Vi when Vi is positive, is minus Vi when Vi is negative. Okay, right? So Vi when Vi is positive, this means the output waveform will look like this. but when Vi is negative, it's negative of that. So again it will look something like this, right? So what's doing, we have just taking the absolute value of Vn, which happens to be option D. Okay, just like in the previous problems, here again we just took two conditions when diode is on and off, and simply we just went ahead and solved the problem, right? So just keep into account that just take the two cases, when D is off and when D is on, and we'll be fine. Correct? So yeah, so that's about that. Moving ahead for the next problem. Okay, so this is the transfer function that is given to us, hs20s over s plus 100 over s plus 1000 at frequency of 2 Hz. We are required to find the phase. Okay, so we are required to find the phase of it at f equal to 2 Hz. Okay, so first let me reduce it to a form in which we can understand, we are habitual of seeing it. So I'll write as 20s over, I'll take 100 common from this, and I'll take 1000 common from this. Okay, and I'll write it 10 to the power 2 into 10 to the power 3, just taking it common. So this will come out to be 2 into 10 to the power minus 4 s 1 plus s by 100 and 1 plus s by 1000, right? So remember, this is in j omega terms, right? And this is given in f terms. So first I'll try to find out its corresponding frequency, that is 2 pi f. This will be 2 into pi, that's 3.6.28 times 2, so let's approximate it as 12.5 radian per second. So omega is 12.5 radians per second. Okay, so we know that what we know about phase. So remember, so now I am writing it as k. S I can write as j omega. This k is this term, and I am writing is 1 upon j omega by omega 1 plus j omega by omega 2. Okay, where omega 1 is 100, omega 2 is 1000, both in radian per second. Now if you see, let's compare omega and omega 1. Omega is less than omega 1, correct? Omega is less than omega 1. Actually it should be 125, but I'm just, for the sake of this problem, we are simplifying it. This is the Bode approximation. Using Bode approximation, I can say that phase must be 0 degrees, because this is much less than the 3 dB frequency, the applied frequency. Similarly, omega is less than omega 2, because omega is 12.5, omega 2 is 1000. So again I'll assume phase at 0 degrees. So what I'll write, I can write as h of j omega, which is nothing but this is nothing, the phase of k is 0. So phase of k plus phase of j omega plus phase of 1 upon j omega by omega 1 and plus phase of j omega by omega 2. So these two are 0 by Bode approximation. Phase of k is a constant, this is again a 0, right? So only thing, the phase of j omega, which is nothing but 90 degrees, because this is a purely complex term, and complex term has phase of 90 degrees, correct? So for problem 9 we get our answer C. Very straightforward problem. For the transfer function at a given frequency, you find out omega and you simply compare it to the values of the 3 dB frequencies that we have in the problem, and then you can just using this expression you can break it down like this and solve it out. Okay, right. So now moving on to the next problem. Now we are obtained to same problem, but we are this time at 4 kilohertz. Okay, so f is 4 kilohertz. I'll obtain omega first, 2 pi f. So that will come out to be 8 times pi, that comes out to be around 25 kilo radian per second. Okay, so I'll write this as again in terms of j omega. This is the same problem that we had before. Okay, remember that. So it came out to be 2 into 10 to the power 4 j omega, 1 plus j omega by omega 1 and 1 plus j omega by omega 2. Remember, omega 1 was it 100 radian per second, omega 2 was 1000 radian per second. Now let's compare omega with omega 1 and omega 2. Now again I can write phase of j omega will be nothing but phase of k plus phase of j omega plus phase of 1 of j omega by omega 1 plus phase of j omega by omega 2. This phase is 0, this is 90 degrees, right? Let's try to find out this phase. Okay, so for that I'll compare omega with omega 1. I can see that omega is greater than omega 1. Omega is 25 kiloradians, this is 100, this is much greater, and this is 100, this is 10 to the power 4 approximately. This implies phase will be minus 90 degrees using Bode approximation. So this is how it looks like actually. At omega naught, this is 0.1 omega naught, this is 10 omega naught. So phase is 0 earlier, and then it goes down, and then it saturates at 90. So this is 0, 40, minus 45, minus 90. This is for poles, and yeah, single order poles, and this is the phase. So at much lower frequencies it's 0. At omega naught it's 45, minus 45, and at greater than 10 omega naught is minus 90. Here omega is greater than omega 1, so it will be minus 90. Similarly, let's compare omega with omega 2. Omega is 2.25 kilo, this is 1 kilo, 25 is greater than 1. So this phase will also come out to be minus 90 by this Bode approximation. So let's add the total phases. 0 plus 90 minus 90 minus 90, this will come out to be minus 90 degrees. Option A. Again a very straightforward problem. Okay, just compare the values of the frequency of the given frequency with your 3 dB frequencies omega 1 and omega 2, and you can use the Bode approximation to arrive at the phases. Okay, so now we are required to find the slope of the magnitude Bode plot. Okay, so this is that, and this time the frequency is 0.5 kHz, 500 Hz. Sorry, this is the frequency. So again I'll try to obtain the omega 2 pi f. So that will come out to be approximately 3 kiloradian per second. And I'll again write the expression for this. This was coming, remember, this was coming out to be 2 into 10 to the power minus 4 j omega 1 plus j omega by omega 1 plus j omega by omega 2. Now let's just quickly talk about the magnitude plot. So if this is some frequency omega naught, 3 dB frequency, and this is 0.1 omega naught, this is 10 omega naught, what happens is that this is the magnitude mod h in dB. So effectively 20 log mod h. Okay, it remains constant till omega naught, and then it keeps on falling at 20 dB per decade. So if let's say this value is 30, right, here it will be 10, and then if we go to 100 omega naught, this value will become minus 10. I am talking about a single order pole. Single order pole means the expression is something like this: j k 1 plus j omega by omega naught. So you can see the slope here is 20 dB per decade because there is only one pole, single pole. Okay, so we just need to compare the given frequency with the 3 dB frequency. So given frequency here is 3 kiloradians per second. So let's compare them. Okay, yeah, so that's how it will be. And the slope for this j omega, right, the slope for this j omega is 20 dB per decade rising. So we can say that if h equal to j omega, this implies slope equal to plus 20 dB per decade. This is minus 20. See, it's reducing. Okay, so at 3 kiloradians, so I'll just compare omega with omega 1. Okay, so what I can do is that, yeah, so I'll try first compare omega with omega 1. So omega is 3k, so omega is greater than omega 1. Omega 1 is nothing but 100, this is 100, this is 1000. Okay, if omega is greater than omega 1, this implies slope of minus 20 dB per decade, because see, this value is 100 and we are operating at 3 kilo, we are operating more than 10 times, so we have crossed it. Similarly, if omega, let's compare to omega 2. So omega is greater than omega 2. Omega 2 is, this is omega 2, this is omega 1. So omega 2 is 1000 and omega 1 is 100. This will again give us a slope of minus 20 dB per decade, because slope changes at omega naught. This is the Bode approximation. So omega naught here, in this case, is omega 2. So at 1 kilo radians per second, the slope will change. Okay, so what is the total slope? The constant does not have any slope. So slope will be equal to, slope of mod h will be equal to slope of j omega plus slope of 1 plus j omega by omega 1 plus slope of 1 plus j omega by omega 2, and at this frequency. So this is, I told you, is plus 20, this is minus 20, this is again minus 20. So overall it will be minus 20 dB per decade. Okay, so it should be minus 20 dB per decade, which is option B. Again, straightforward problem. You find out the 3 dB frequencies omega 1 and omega 2, and you compare with the given frequency of 3 kiloradians per second. If it's greater, then you will have a minus 20 dB per decade, because they're in denominator, they are poles. In the numerator, there is a 0, right? J omega term. It will always have a slope of, because it's directly proportional to omega, correct? So it will have a positive slope of plus 20 dB per decade. This is also talked about in the lectures. You can refer that for more details. Okay, so same problem, but this time the frequency is 100 Hertz. Quickly do that. F equal to 100 Hertz. Omega will be 2 pi f. So this will come out to be 200 times, so it will approximately be around, let's approximate it to be 600 radians per second. Okay, and I write this again down as 2 into 10 to the power minus 4 j omega 1 plus j omega by omega 1 plus j omega by omega 2, correct? Omega 1, remember, was 100, omega 2 was 1000. And again, remember this thing for poles. This is single order poles, right? This is omega naught, 3 dB frequency. This is mod h, poles, first order. Okay, so if you cross the 3 dB, if the given frequency, this is frequency, by the way, in the last time also, so everywhere is the frequency here. Okay, so if the frequency crosses 3 dB frequency, then you will have a minus 20 dB per decade. So let's see. So omega, which is 600, is greater than omega 1. So this implies a slope of minus 20 dB. Here, omega, which is 600, is less than omega 2. This means you are somewhere here. So it will have 0 slope, 0 dB per decade. So what is the total slope? Total slope will be slope of j omega plus slope of 1 plus j omega by omega 1 and plus that of 1 plus j omega by omega 2. This will be 0, we just saw. This is 9, sorry, not 90, plus 20 for j omega, plus this is minus 20. So overall slope will be 0 dB per decade. This is happening because omega 2, so omega naught is here, but omega 2 is here, right? This omega naught you can see, think it as 600. Oh, sorry, I made a mistake. 1 second. Yeah, no, yeah, I'm correct. It's fine. So omega 2 is equal to 1000, right? So this means omega 2 is somewhere over here, but you are applying a frequency of only 600, so you are applying only this frequency here, so there will be no slope. It's 0 dB per decade. So total will come out to be 20 plus minus 20 equal to 0, which happens to be option A. Okay, similar problems, just that the frequency we are changing, and you have to use the Bode approximation to arrive at the correct result. Okay, moving on to the next problem. Which of the following transfer functions correspond to the magnitude Bode plot shown in the figure? So this time we are given the Bode plot and we are required to find the transfer function. Okay, so first you can see that for low frequencies, right, it's rising at you can see the slope here is 20 dB per decade. So I'll write this information. For omega less than 10 units a radians per second, slope is plus 20. Secondly, for omega greater than equal to 10, slope equal to 0. What would have happened? This means there must be a pole at this, because remember, only poles introduce negative slope. So if you already have a positive slope, if you introduce a negative slope, the total slope will become 0. We just saw in the last problem. Okay, so what this means is that using this information, this implies there is a pole at omega equal to 10 radians per second. Okay, and so this is the first piece of information that I can obtain. Second, there is a j omega term in numerator. Why? Because the slope at low frequencies is plus 20 dB per decade, and plus 20 dB can be introduced by this term, j omega term. Okay, so this implies my function would be of the form some constant k j omega 1 plus j omega by 10. You can see that this will introduce a pole at omega equal to 10 with that will introduce a slope of minus 20, and this has a plus 20. So after this point there will be 0 slope, which we can see here, right? So now what I'll do is but we need to find the value of k. How do you find the value of k? What I'll do is that I'll take some omega greater than 10. Okay, so what I'm doing is that effectively is I am taking so what I'm doing is that so I'm taking only this value. So what will happen, let's analyze at omega greater than 10. Let's say let me do this again. So what I mean to say is that, so this is the form that we have obtained, but we also need to obtain the value of k. So now let's take omega equal to 100. If omega equal to 100, so what's going to happen? I can write this k j omega. If it's 100, I can ignore the one term, so it will be j omega by 10, because this will be something like 10j. It's much greater than 1. J omega gets cancelled, so I get is just 10k. So h is coming out to be at 10 times k, some constant k, and I know the magnitude is 20 dB. Okay, at omega equal to 100. Okay, so I can say that this implies 20 log 10k equal to 20, because remember this is the point that I put this value equal to 20. This will give me log 10k equal to 1. 10 to the power 1 is 10. Okay, so 10k will come out to be 10 to the power 1, right? Correct. So this will give me k equal to 1. So I have obtained k equal to 1, and this I'll put in this expression, k j omega 1 plus j omega by 10. This will give me j omega by 1 plus j omega by 10. This is 10 j omega by 10 plus j omega. J omega is s, so 10s upon 10 plus s, right? Option B. The key thing to note that just identify the points where the slope is changing. That's your pole, or 0 depending. So here the slope was rising, but then it became flat. The reason is that there must be a pole at omega equal to 10. Hence we introduce this term. But for low frequency it was rising. This means it's a 0 at j omega. And finally we put a constant k, which we obtained the value by putting you can use any of these values for that matter. You can obtain this, you can put omega equal to 1 also, anything that you need to just solve it. And I just solved it for omega equal to 100, obtained the value of k equal to 1, and we got 10s over 10 plus s. Alright, now again this is a similar problem as before. Here we are required to find the transfer function corresponding to this given magnitude Bode plot. Okay, so I'll see identify the points at which the slope changes. The slope changes here and slope changes here. So what I'll do, this means omega 1 equal to 10 and omega 2 equal to 100. Okay, so omega 1 equal to 10, right? And I can see that the frequency, that the slope is rising. Okay, what this would mean is that at omega equal to 10 it must be a 0, right? Then only the slope can rise. Or the other thing that can happen is that wait, no, that's the case. So at omega 1, what I am going to have, sorry, but where was it? Yeah, at omega equal to 10 I must have a 0, then only the slope can rise. Okay, so this implies that and I notice that slope is rising after omega 1 at 20 dB per decade. So this implies single order 0. How do we write single order 0? In this format. So I can write this as, this is the wave function, sorry, transfer function of this form. At omega t equal to 100, I notice that the slope has reduced. Slope reduces from 20 to 0. This would mean introduction of minus 20 dB per decade. This is per decade. What does this imply? This implies a single order pole. How does the form look like? It will look like j omega by frequency is 100 by 100. And we know that once we have obtained the two functions, let's call them h1 and h2, I can simply multiply them. So h omega will be k h1 omega h2 omega j omega, sorry about that. So it will be k 1 plus s by 10 1 plus s by 100. That is the form that I'll obtain. Now you take the LCM, it will be, just a second, let's just analyze for lower values what will happen. For omega less than 10, for omega less than 10, this would be constant, right? This would be constant. And for omega less than 10, let's talk about this. For omega less than 10, let's say omega equal to 1. Okay, so omega equal to 1, so this will be of no relevance. Similarly, this will be of no relevance. Yeah, we should have a constant value, which we are getting a constant value, correct? So yeah, so this analysis is correct. So what I'll get is 10k s plus 10 over s plus 100. This should be the form 10k s plus 10 over s plus 100, s plus 10 over s plus 100, this form. Okay, k is 10k, so you can assume this 10k to be some other constant x. Does the form matter? So s plus 10 over s plus 100. Key thing to note is that, again, look at where the slope changes in magnitude Bode plot. If the slope is rising from there, this means it's a 0. If the slope is reducing, it's a pole. And also note the value. So if the slope changes plus 20, you can say the slope is plus 20 here, right? Because 25 minus 5. So this means a single order. Again, 20 to 0, this means single order pole. So these are the things you need to take care. So in the transfer function of Q14, what is the value of k? Okay, brilliant. So what we had obtained was, remember, we had obtained hj omega as some constant k. I'm writing it as x times 10 plus s. What was the answer? Yeah, 10 plus s over 100 plus s. Okay, so we need to find this value x. How do you find the value of x? I already told you. There are multiple ways of doing it. So what I'll do is that I'll put x as the value of omega. I'll choose this. Okay, I call it omega equal to 1. So put omega equal to 1. So I'll get j omega at omega equal to 1, all in magnitude. Okay, x times, so I'll write it as j omega plus the value of this is 10, j omega plus 100, correct? And I put omega equal to 1. This value is 5. Okay, 20 log dB. So let's just evaluate this expression. This is x mod x. Okay, j omega plus 10. So if I put omega equal to 1, this will give me 10 plus j over 100 plus j. modulus. So this is j times 1. This is much smaller as compared to 10, so I can only take 10. So I'll put it 10. Similarly over 100, this comes out to be mod x over 10. Mod x over 10. So what I'll do is 20 log of this. 20 log of x by 10 is what? 5. 20 log of x by 10 is 5. So this will give me x by 10 equal to 10 to the power 5 by 20. Okay, so 10 to the power 5 by 20 is 1.78. I multiplied by 10, I get 17.8. The value of x that I am obtaining is 17.8. Remember, this was the expression x times s plus 10 over s plus 100, and x I obtain as 17.8, which is option D. Again, very simple way, just put omega equal to 1 in this expression, use the Bode approximation, and you will get 20 log, do that, and you will get x as 17.8. Okay, next, yeah, so this question asks, which one of the following transfer functions correspond to the phase Bode plot shown in the figure? So now this time we are given a phase plot, and we are required to find the form of the output, how it looks, of the transfer function, sorry. Okay, so this is the key thing to note here is that first of all, you notice that what is the 3 dB frequency. First thing, note 3 dB frequency. We notice this is the 3 dB frequency. In magnitude plot, where there is a kink, where the slope changes, that's the 3 dB frequency. In phase plots, where it's in the middle of the two slopes. Okay, so 1 and 100, it must be in the central part, right? Omega equal to 10. So we see that it is omega equal to 10. At omega equal to 10, units are radians per second, right? Check whether slope is positive or negative. Slope is positive or negative. We notice that it is negative. Negative slope denotes pole. Okay, negative slope will mean there is a pole. In the standard format I'm talking about, there can be many different flavors. And finally, check the magnitude of slope. So we can see that it's sweeping from 0 to minus 90. This means it's a single order pole. Single order. Negative sign means it's a negative, it means it's a poles, and 0 to 90 means it's single order. Okay, so this means now using all this information, I can write that this is some constant k over 1 plus j omega over the value is 10 raised to the power 1. Why 1? Because it's single order. Why denominator? Because it's a pole. And the value of omega, the omega naught, which we say, the 3 dB frequency is 10, which I have noted it over here. So this is the format that we notice. K 1 plus j omega by 10. Is there an option like that? K single pole. Yeah, this one. So you can, I'll write this here. K 1 plus j omega by 10. This is h. In terms of s format, I can write it as k 1 plus s by 10. Take LCM, so it will be 10k over 10 plus s. So some constant over s plus 10, which is the format A. So that is the way to do it. I have not been able to discuss one problem in the class. So if there are any comments or questions, you can ask. What I'll try to do is when I'll upload the video on YouTube, then I'll add that question. So for the live session, I think we are out of time, so I'll not extend it, but I'll solve this and upload it, so you need not worry about that. So in just to summarize, in today's class we had talked about some when we introduce diodes to op-amp. So how diode is on and off, and how the input how the output waveform may look like in terms of input, that we saw. And then finally we solved quite a few problems on magnitude Bode plot and phase Bode plot, both flavors. That is, you are given the transfer function and you are required to plot the magnitude and phase Bode plot, and vice versa. That is, you are given the plot like in this problem and you are required to find the transfer function. So we saw both the flavors, and it's important that you analyze that, because the practical application for op-amps is sometimes to design filters. like we saw one problem where we saw it's a low pass filter. So in that sense you must understand, at least you have a basic idea about how the poles and zeros, how do they work, single order, double order, and so on. So it gives you an idea for to design a good circuit. So that's all. So that's all from me for today. I'll stop presenting now, and if you have any comments, you may ask.